If space exploration feels ordinary today, it is only because we no longer grasp how extreme it truly is. The moment we confront real distances, real energy demands, and real scale, that illusion collapses. A simple comparison is enough. Take a Lego astronaut minifigure and scale it correctly to the Saturn V rocket. The rocket becomes more than 60 times taller than the figure. This is not symbolism, it is literal reality. Saturn V stood 111 meters tall and remains the most powerful rocket ever built by humans. Its 5 F1 engines produced roughly 33,000 kilonewtons of thrust, enough to lift nearly 3 million kilograms while fighting gravity, atmospheric drag, and immense structural stress at the same time. At launch, the noise reached around 194 decibels, approaching the physical limit of sound propagation in Earth's atmosphere. Beyond that point, louder sound ceases to matter because the air itself cannot carry it. Yet almost all of this power served one purpose only: leaving Earth. Tens of tons of fuel were burned not to travel through space, but merely to climb out of the planet's gravity well and reach orbit. Once in space, the rules change completely. There is no friction and no natural braking. Motion persists indefinitely. If you accelerate, you will keep moving forever, unless you expend the same amount of energy to cancel that motion. This is why space travel is not about speed. It is about energy. Every kilogram you want to move must be lifted by fuel. But that fuel also has mass, and that mass requires even more fuel. This creates the harsh feedback loop known as the tyranny of the rocket equation. Carry more fuel to go farther. And you need exponentially more fuel just to lift the additional fuel itself. This single principle explains why humans have not returned to the moon since 1972. It explains why interplanetary travel remains slow, expensive, and rare. During the Apollo era, launching 1 kilogram into orbit cost roughly $60,000. Even today, despite enormous technological progress, escaping Earth remains the most difficult and expensive part of any mission. Modern rockets like Falcon 9 have reduced costs to a few $1,000s per kilogram, and Starship aims to lower them even further. But none of this changes the deeper truth. Rockets are not fighting budgets. They are fighting physics. Before we can seriously dream about Mars or distant stars, we must first understand the prison we are trying to escape. Gravity is not merely an obstacle. It is the gatekeeper. And so far, it has never been impressed by human ambition. Space travel is not limited by distance alone. It is limited by energy. Every journey beyond Earth begins with a brutal truth. Getting into orbit is harder than traveling through space itself. Almost all the fuel of a rocket is burned in the first minutes after launch. Gravity is the real enemy because escaping it requires enormous force. Once a spacecraft reaches orbit, the rules change completely. Friction disappears. There is no air to slow you down, no natural braking force. Motion becomes permanent unless engines are fired again. If a spacecraft accelerates once, it will keep moving forever. To stop, it must burn fuel in the opposite direction. Slowing down is just as expensive as speeding up. This simple fact defines everything about spaceflight. It is why rockets look the way they do. It is why most of a rocket's mass is fuel, not payload. The rocket equation creates a trap that engineers cannot escape. Every kilogram of fuel requires more fuel to lift that fuel. Mass grows exponentially, not linearly. This means chemical rockets waste enormous energy just to carry their own propellant. During the Apollo era, launching 1 kilogram into orbit cost more than $60,000. This was not because of inefficiency or poor engineering, but because physics demanded it. That cost is the main reason humans have not returned to the moon since 1972. We did not lose the technology. We lost the economic justification. Modern rockets reduced costs, but not the underlying problem. Reusable boosters lowered prices, not physical limits. Falcon 9 brought the cost down to a few $1,000s per kilogram. Starship aims to go even lower, but it still relies on chemical propulsion. The same basic method used since the mid-20th century. The tyranny of the rocket equation still applies. Traveling to Mars with chemical rockets takes 7 to 10 months. During that time, astronauts face radiation, isolation, and physical degradation. Muscles weaken. Bones lose density. The longer the journey, the higher the risk. To travel farther, faster, and safer, humanity does not need better rockets. It needs entirely different ways to move through space. Chemical rockets are powerful, but they are fundamentally limited. They burn fuel through chemical reactions that cannot exceed strict energy thresholds. No matter how advanced the design becomes, chemistry has a hard ceiling that cannot be crossed. This limitation is known as the tyranny of the rocket equation. Carrying more fuel always requires even more fuel to lift that fuel into space. At a certain point, adding energy only makes the vehicle heavier instead of faster. This is why chemical propulsion becomes inefficient for missions beyond Mars. Travel times grow, dangerously long as distance increases. Human survival becomes the primary challenge, not navigation or guidance. Radiation exposure, isolation, muscle loss, and bone density reduction intensify with every additional month spent in space. These risks grow faster than our ability to mitigate them with shielding or medicine. This is why scientists began searching for propulsion methods that do not rely on chemical bonds. Nuclear reactions release millions of times more energy than chemistry. In theory, this makes far shorter and faster missions possible. One of the most extreme ideas was Project Orion. It proposed accelerating a spacecraft using a series of controlled nuclear explosions detonated behind it. Each explosion would strike a massive steel pusher plate, transferring momentum and pushing the ship forward. The physics behind Orion worked. The engineering challenges were solvable. The danger was political and existential. A single launch failure involving nuclear devices could contaminate large areas of Earth. Because of this risk, the concept was abandoned despite its effectiveness. A safer alternative emerged in the form of nuclear thermal propulsion. Instead of explosions, a nuclear reactor heats hydrogen to extreme temperatures. The rapidly expanding gas produces thrust far more efficiently than chemical engines. Nuclear thermal rockets could cut travel time to Mars nearly in half, shorter. Missions reduce radiation exposure and physical degradation of the human body. The technology was tested during the Cold War and proven to work. However, safety concerns, public fear, and international treaties halted its development. Once again, physics allowed progress, but human factors stopped it. As a result, humanity remains bound to slow chemical propulsion, even though faster paths through the solar system are physically possible. Solar sails offer a radically different approach to space travel. Instead of burning fuel, they use the pressure of light itself. Photons have momentum, and when they strike a reflective surface, they transfer that momentum forward. This thrust is extremely weak, but it never stops. Over time, constant acceleration allows a spacecraft to reach high speeds without carrying fuel. This makes solar sails ideal for long-duration missions where patience matters more than raw power. The concept is not science fiction. In 1973, the Mariner 10 probe used solar radiation pressure to adjust its trajectory. Modern experimental sails have already flown successfully. Unlike rockets, solar sails grow faster the longer they travel. However, near Earth, sunlight is too weak to provide rapid acceleration. To overcome this, scientists proposed using powerful lasers. A ground-based or orbital laser array could push a sail far harder than sunlight alone. In theory, this could accelerate a probe to a significant fraction of the speed of light. Such a system would allow interstellar travel without onboard fuel. This idea forms the basis of projects like Breakthrough Starshot. The target is Alpha Centauri, the nearest star system to Earth. Even at 10% of light speed, the journey would take over 40 years. For humans, this is still impractical. Life support, radiation shielding, and psychological endurance become overwhelming challenges. At relativistic speeds, time itself begins to behave differently. Due to time dilation, travelers would experience time more slowly than observers on Earth. Decades. For the crew could mean centuries passing at home. This creates a strange future where explorers return to a world that no longer remembers them. Interstellar travel is not only a technical problem, it is a human one. Chemical rockets pushed humanity beyond Earth, but they are now approaching hard physical limits. Every kilogram of fuel requires additional fuel to lift it, and that fuel also needs fuel. This exponential burden is known as the tyranny of the rocket equation, and it defines how far chemical propulsion can realistically take us. With current engines, a journey to Mars lasts between 7 and 10 months. During that time, astronauts face constant radiation exposure, progressive muscle and bone loss, psychological strain, and the risk of system failure. Shortening travel time is not about comfort, it is about survival. That reality forced scientists to look beyond conventional rockets toward far more radical propulsion concepts. One of the most extreme ideas ever proposed was Project Orion. Instead of a traditional engine, the spacecraft would be propelled by a series of controlled nuclear explosions detonated behind it. Each blast would strike a massive pusher plate, transferring momentum through shock absorbers and pushing the ship forward. On paper, this method was astonishingly powerful. Orion-class vehicles could theoretically reach Mars in days rather than months, and even make interstellar missions conceivable. However, the concept carried unacceptable risks. A launch failure involving nuclear devices could contaminate large areas of Earth with radioactive material. For this reason, despite its technical feasibility, Project Orion was abandoned. A safer alternative emerged in the form of nuclear thermal propulsion. In this system, a nuclear reactor heats hydrogen to extremely high temperatures and expels it through a nozzle to produce thrust. There are no explosions and no radioactive exhaust released into the environment. This approach can double the efficiency of chemical rockets, significantly reducing travel time to Mars. Nuclear thermal engines were successfully tested during the Cold War and proved to work as expected. The technology itself is mature, but political concerns, safety regulations, and public perception halted its deployment. Today, as deep space missions become more realistic, my interest in nuclear thermal propulsion is quietly returning. Beyond nuclear fission lies an even more ambitious goal. Yes, fusion propulsion. By fusing atomic nuclei, a spacecraft could access enormous amounts of energy with relatively small amounts of fuel. In theory, this would allow rapid travel across the solar system and open the door to truly fast exploration. The problem is controlled fusion. Reactions are extremely difficult to stabilize even in large ground-based facilities. Building a compact, lightweight, and reliable fusion engine remains one of the greatest challenges in physics and engineering. These propulsion systems will not appear overnight, but without them humanity remains trapped by slow journeys and narrow reach. If we want to expand beyond nearby planets and seriously approach the stars, we must first learn how to control energy on a scale we have never mastered before. Space exploration ultimately confronts humanity with limits that are not only technical, but existential. Every propulsion system we have discussed, from chemical rockets to nuclear engines and solar sails, faces the same fundamental question of scale. Space is not just large, it is brutally vast. Distances are measured not in kilometers, but in light years, and even the fastest concepts we can realistically imagine still move at a crawl compared to cosmic scales. This means that interstellar travel is not a problem of ambition alone, but of time, energy, and human endurance. At relativistic speeds, time itself becomes an obstacle. For travelers moving close to the speed of light, time would slow down relative to Earth, allowing them to experience decades while centuries pass at home. This is not science fiction, but a direct consequence of Einstein's relativity. However, this creates a future where explorers do not return to the world they left, but to a civilization that has moved on without them. Interstellar missions therefore challenge our ideas of continuity, identity, and purpose. Beyond physics, there are biological and psychological limits. Humans evolved for Earth-long-term exposure to radiation, low gravity, and isolation damages the body and mind. No propulsion system solves the problem of maintaining life for generations inside a closed spacecraft, or the mental strain of knowing that Earth is forever out of reach. These challenges have led some scientists to propose robotic exploration as the most realistic path forward. Machines do not age, do not suffer isolation, and can survive environments that would instantly kill humans. In many ways, our probes are already our interstellar ambassadors. Yet this raises another question. If machines explore the universe for us, what is the role of humanity itself? Space exploration has never been only about reaching destinations. It is about understanding our place in the universe. The same physics that limits our reach also reminds us how fragile and rare life is. Every advancement in propulsion shows us that Earth is not small, but precious, an oasis in a hostile cosmos. The future of space travel may not be defined by conquering the stars, but by choosing carefully how and why we reach for them. We are a young species at the very beginning of cosmic awareness. Our technology is powerful, but incomplete. Our curiosity is immense, but our responsibilities are greater still. Space does not promise answers. It offers perspective. And in that perspective lies perhaps the most important discovery of all.